In this chapter, we're going to spend our time analyzing quadratic functions. In this lesson, we're going to focus specifically on the factored form of the quadratic function.
All right, hi everybody. So in a previous lesson we introduced this idea of a factored form of the quadratic function, okay, where m and n, when it's written like this, both represent the roots or the x-intercepts of the function. Okay, and remember in standard form it's written as ax squared plus bx plus c, but that can be factored, which is why we call it factored form, out like this. Now you can't always do it really simply to put it in this form. Sometimes you got to use the quadratic formula to get there. But anyway, quadratics can be written in this form right here, where a, m, and n are all considered what we parameters of the graph. And remember what a does. A tells us which direction it opens. If it's positive, it opens up. If it's negative, it opens down. And m and n, like we said just a moment ago, are going to be the x-intercepts of the graph. Now, one of the neat things about a parabola is that it has a symmetry to it. Okay, it has bilateral symmetry. Okay, left side and right side are identical, mirror images of each other. So the axis of symmetry passes right halfway between the two x-intercepts. And if you just think about what it looks like, that actually makes perfect sense. Okay, so think about your parabola right here. Okay, and let's say here's the x-axis. Well, that vertex is going to be right smack dab in between the two of them. And so as a result, if we know the x-intercepts, what we can do is we can get the axis of symmetry simply by taking the average of the two x-intercepts. And actually, I'm going to take this one step further. Okay, so let's, in a previous lesson here, we had used the letter h as the x value for the vertex. So m plus n over 2 is going to give us h. Okay, and there's our axis of symmetry. Notice that k, which is the y-coordinate of the vertex, is simply going to be the function now evaluated at h. And so what I've got right now is a really clean way of getting the vertex if I know the two x-intercepts. Oh, and the function, by the way, you got to know the function here. So, and I'll show you that in just a second here. But anyway, let's take a quick look at some examples of how we might apply that information to a whole series of questions. Okay, so here we go. So what I'm going to do is I'm going to run through, I'm going to take a look at each one of these functions down here, and I'm going to identify the different pieces here. And then from that, we're going to determine other aspects of this particular function here. So right now, and a is going to be that leading coefficient right there in front, and if there's nothing there, I know it's a 1. M, very common to want to grab the negative out of this and say m is negative 2, but notice that in factored form that subtraction is there already. That subtraction and that subtraction, those are parts of this factored form. So this isn't negative 2, this is positive 2. Just like here, for n, that's not going to be negative 8, that's going to be positive 8. So my two x-intercepts here will be 2 and 8. Now, and again, don't put parentheses around those when you're just listing off x-intercepts. As soon as you put parentheses around that becomes a point where that's your x-coordinate and that's your y-coordinate. Right now, this is just a list of two numbers here. Now, we want to come up with the x-intercept. Okay, sorry, x-intercept, the y-intercept. Well, that's pretty easy. I'm just going to substitute 0 in for x. So 0 minus 2 multiplied by 0 minus 8. So it's going to be negative 2 times negative 8, positive 16. So my y-intercept will be positive 16. The next thing I'm going to ask you for here is your axis of symmetry. Now remember how that works. The axis of symmetry is going to be the average of the two x-intercepts. So 2 plus 8 over 2. And I'm giving myself a little bit of room here because I want to take this one step further. Well, 2 plus 8 is 10 over 2 is 5. So the axis of symmetry is going to be x equals 5. Now, knowing that, I'm actually going to add one other little bit of information here. If you take the 5 back into this function right here, if we do 5 minus 2, that's going to be 3. 5 minus 8 is going to be negative 3. 3 times negative 3 is going to be negative 9. So right there, I've been able to determine the vertex. The vertex is going to be 5 comma negative 9. That's kind of neat. Okay? I like the fact that having the function in factored form, I can actually pretty quickly get the vertex if I know what to do with that information. Now the direction of opening this is going to be up because the a value that I have here is positive. Okay, let's take a look at another one. Negative x plus 2 times x minus 6. Well, the a value in this case is going to be negative 1. And actually from there, you know what, let's jump to the end here. As a result, I know that this is going to open down. I don't even have to think about that. I know that automatically. Here, oh, there's a positive sign here. There's a positive. That should have been a subtraction, but now it's been changed into a positive. Well, the only way to change subtraction into this addition is if you're subtracting a negative. So that tells me that the m value here is actually negative 2. Now, that subtraction is just exactly where I expect it to be, so the n value here is going to be positive 6. So my two x-intercepts here are going to be negative 2 and positive 6. Whoops, can't see that. My y-intercept, okay, if I make x equal to 0, that's going to be negative 0 plus 2, 0 minus 6. So we'll do the negative up front here. Last year, 0 plus 2 is 2, 0 minus 6 is negative 6. So 2 times negative 6 is negative 12. With that negative there, makes this positive 12. My axis of symmetry is going to be negative 2 plus 6 over 2. So negative 2 plus 6 is going to be 4, divided by 2 is 2. And now that I know what the axis of symmetry is, I know the x-coordinate of the vertex, so I'm going to put 2 here. I go back to the function. I'm only going to do this, let's say, for the next one, and then I'm not going to bother with the vertex anymore, but I'll do it here. If you plug 2 into this, 2 plus 2 is 4. 2 minus 6 is negative 4. Okay, so 4 times negative 4 is going to be negative 16, and that negative in front then makes it positive 16. And so I know that my vertex is positive 16. Okay, that's awesome. Let's take a look at the next one. Okay, 3 times x plus 2, x plus 6. Well, I know that my a value is 3. And remember, because that's positive, I can jump over here, and I know that this means my parabola is going to open up. Okay, in this case right here, both of these are positive, which means my m value here must be negative 2. My n value here must be negative 6. And so my two x-intercepts here are negative 2 and negative 6. To get the y-intercept, I come back here. I'm going to plug that 0 in. So 3 times 0 plus 2, 0 plus 6. Okay, well, ignore the 3 for right now. 0 plus 2 is 2. 0 plus 6 is 6. 2 times 6 is 12. Ooh, multiply that by 3 and I get 36. So my y-intercept here is 36. Now, I'm going to find my axis of symmetry again by finding the average of the two. So negative 2 plus negative 6 over 2. Negative 2 plus negative 6 is negative 8. Divided by 2 is negative 4. Again, that gives me the x-coordinate of the vertex. Now, this will be the last time that I find the vertex because I'm hoping that you get the idea here. I take that negative 4, I go back to my original function, and we'll multiply by 3 at the end. Negative 4 plus 2 is going to be negative 2. Negative 4 plus 6 is going to be positive 2, and I'm hoping you're seeing a bit of a pattern there. So negative 2, positive 2 is going to be negative 4 times 3 will be negative 12. And so the y-coordinate of the vertex is negative 12, and I know that it opens up. So I'm not going to bother with the vertex anymore. I hope that you're seeing the pattern there, but let me keep going here. Okay, so negative 2x, x minus 4, and I love the fact that this is included in this particular problem here because I really want you to see what happens when you've got something like that. The a value is just the negative 2 right up at the front here, and again I can now jump way over here. That means my parabola is going to open down. Now, this should have had, this x should have been in parentheses, and there should have been something being added or subtracted to it. If that particular binomial collapses down to just an x, that's because the thing that I'm adding or subtracting was 0. Okay, and so I want you to connect that value with that factor when it sits all by itself here. Now x minus 4, again, there's my subtraction, so I know that this n value should be 4, which means my x-intercepts are 0 and 4. Okay, so I hope that makes sense here. Now, my y-intercept will be back when this is equal to 0, when I let x equal to 0, but watch what happens when I let x equal 0. it doesn't matter that what's inside this set of parentheses here becomes negative 4. I am multiplying by 0. I'm multiplying that whole thing by 0. So the answer immediately collapses to just 0. And now for the axis of symmetry, that is just going to be the average of the two x-intercepts. 0 plus 4 is 4 divided by 2 is 2. So the axis of symmetry is x is equal to 2. Oh, you can't see that. I'm sorry. That looks like 2 squared. That's supposed to be just that x equals 2 right there. All right, a couple more here. This one's a little bit different because of that 2 right there, and that can happen. You need to be prepared for that, and I'll show you what to do there in just a second. But right now the a value is 4, and because that's positive, that means way over here this is going to open up. Okay, now my 2x-intercepts here. It's very tempting to want to make this just x equals negative 3. A lot of times people want to put negative 3. They know that that addition shouldn't be there. It should be subtraction. The only way that becomes addition is if it's subtracting a negative, so this is going to be negative. But a lot of times people just stop at bringing the 3 over. Remember, the way you solve that is you're going to take that 2x plus 3 and set it equal to 0. So you bring the 3 over, but then you've got to divide by that 2. And it's just that bit of division that tends to be left out. So this should have been negative 3 over 2. Now, I know that doesn't quite look like my m value. When you compare that to this right here, that doesn't look like your m value. And that's because actually this probably should have been altered just a little bit. Okay? We probably should have taken that 2 out a little bit earlier and really made it fit that form up there. And I'll show you what I mean by that in just a second. But all I'm trying to do right now is give you a sense of how to interpret this. Okay, but I'll in a second here, once I'm done this line, I'll go back and I'll show you what I meant by that particular function right there. The n value here is going to be positive 2. That should be pretty straightforward. So negative 3 over 2 and 2, these are your x-intercepts. The y-intercept, if you make x equal to 0, okay, so it's going to be 4, 2 times 0 plus 3, 0 minus 2. So 2 times 0 plus 3 is just going to be 3. 0 minus 2 is negative 2. This is going to be negative 6 times 4 is going to be negative 24. So over here I know this is going to be negative 24. And then the axis of symmetry is the average of the x-intercepts. So 3 over 2 plus 2 over 2. Negative 3 over 2 plus 2. Well, negative 3 over 2, if you want to think about it in terms of decimals, and I know a lot of people do, that's negative 1.5. So plus 2 is going to be 0.5 divided by 2. So it's like 1 over 2 divided by 2 is 1 over 4. And you can verify that with your calculator if you like here, but that means that our axis of symmetry is going to be x equals 1/4. Now, let me show you really, really quickly what I had meant by putting that into factored form. What we probably should have done with this one right here, and I'll grab by my little sticky here. Okay, look, my little mathematics council sticky. Our function here was 4, 2x plus 3, x minus 2. Now, that isn't actually in this form because there should be a coefficient of 1 here and a coefficient of 1 here. So one of the things that I could have done with this, and probably should have done, although your teachers are very likely not going to push you for this, is we probably should have factored out that 2 from here. Now I know when you look at that you think, well, wait a minute, 2's not common. Yeah, I know, but this is what you would do. I'm going to divide out the 2 from both of those terms. I'm going to write it out front here, and when you divide 2 out of the 2x, it's just going to be x. When you divide 2 out of the 3, oh, that doesn't go out evenly, so I'm just going to leave that as a fraction, 3 over 2. So now bear in mind, if you ignore everything, if you now multiply 2 by x plus 3 over 2, that takes you right back to this 2x plus 3. So like I haven't done anything really significant here. It's the same expression overall. I've just changed the way it looks. But now I would multiply that through and I would get 8 x plus 3 over 2 x minus 2. Okay, so really the a value here should have been 8, m should have been negative 3 over 2, n should have been 2. The reason I can kind of get away with doing it the way I did it here is because All I'm really interested in about the a is whether it's positive or negative, whether the function opens up or down. And notice that that didn't change anything, okay? Additionally, one of the reasons we don't typically force you to go this far here is, even as teachers here, we're not thrilled with the idea of having those fractions in there. It is, for a lot of people, it's very intimidating, so we tend to kind of avoid that, okay? It looks better. It looks better, I think we can all agree, when it's written like this than when it's written like this, even though technically this is more in line with the form that we're asking for. Now let's just do this last one here. Negative x minus 10, x plus 10, so the a value is negative 1. I can jump ahead, that means this is going to open down. Okay. My m value is going to be 10, my n value negative 10, which means my x-intercepts are 10 and negative 10. Whoops, almost forgot the negative there. My y-intercept, if you plug 0 in, 0 minus 10, 0 plus 10, that's going to be negative 10 times positive 10, so negative 100. And that negative in front there is going to make that positive, so positive 100. X is going to be the average of the two, so it's going to be, positive 10 plus negative 10 over 2. So that's going to be 0 over 2. So the axis of symmetry is x is equal to 0, which basically just tells me that the vertex is on the y-axis. It didn't get moved left or right. Okay, so I hope that makes sense. I hope in particular that this one right here made sense in terms of what I want you to do. It's not exactly written in the form that I would like it to be, but that's okay. We're going to be a little bit more relaxed on the rules for that because we like the way this looks better than the way it would look otherwise. Okay, everybody. For this next question, it's supposed to be a matching question, but I've actually I've kind of beaten my colleagues to this particular question here. Here are the functions, and we're supposed to match them to the graphs. Well, the graphs aren't here. So what I'm going to do here is we're just going to walk through really quickly, and we're going to graph these things, okay? So let's take a look, for example, at function 1 here. I know, first of all, that it opens up. Secondly, I know that my x-intercepts are going to be positive 1 and negative 4. And I'm hoping that we're getting more and more comfortable with this, okay, that you can just see by basically just changing the sign of the number that's in that binomial. Now, my h value, the h value of my vertex is going to be the average of those two, okay? So 1 plus negative 4 will be negative 3 over 2. Negative 3 over 2. So now what I want to do is I want to come up with the k value, okay? The k value of my vertex there. So basically, what I'm going to do is I'm going to take this negative 1.5, and it might be easier right for the moment here just to think of this as negative 1.5. I'm going to plug that in. So, and I'll do this on a little sheet of paper over here because I don't have a ton of room here. So this is going to be 2 times negative 1.5 minus 1 times negative 1.5 plus 4. Okay, well that's going to be 2, negative 2.5, and then negative 1.5 plus 4 is going to be another positive 2.5. Okay? I do actually prefer to work with fractions, but I know that some people won't here. This is going to end up being negative 6.25. And then when you multiply by 2, that'll be negative 12.5. Okay, so there's the y-coordinate of my vertex here. It's going to be negative 12.5. And there I go. So I want a graph that opens up, has x-intercepts of 1 and negative 4, and has a vertex at negative 1.5, negative 12.5. So let's just put this over here. So if this is my my y axis, this is my x-axis, I know that I'm going to have x-intercepts here at 1, and then 1, 2, 3, 4, negative 4, and that my axis of symmetry goes through negative 1.5, and then way down here at negative 12.5, that's going to be where my vertex is. So this thing's going to open up. I'm going to open up like that. Okay, perfect. Now I could have found the y-intercept as well, but this is good enough for right now to just get a good look at the graph here. Okay, let's look at this next one here. First of all, I know that this one's going to open down. because of the negative in front. I know that the x-intercepts here, and I'm going to do this down to give myself a little bit more room, my x-intercepts are going to be positive 4 and negative 1 this time. Now that means that my h value, okay, my h value here is going to be the average of those two. So this is going to be 4 plus negative 1, which is 3 over 2. So my h value will be 3 over 2, or positive 1.5. Now, again, I'm going to go back in and I'm going to figure out what my k value is for my vertex. So that's going to be y is equal to negative of 1.5 minus 4 and 1.5 plus 1. So negative, that's going to be negative 2.5, and this will be positive 2.5. And notice how every time I do this, I get this repeated value where one is positive as one and one is negative. And that's interesting. The negatives are going to cancel, and 2.5 times 2.5 is going to be 6.25. And so that is the k value of my vertex, 6.25. And let's graph that one here. Okay, y-axis, x-axis. This is going to have x-intercepts here of negative 1, and then 1, 2, 3, 4. It's going to have that axis of symmetry at 1.5, and then up here at 6.25, and this thing's going to open down. Oh boy. Okay, my scale is wildly out of control, but you get the idea. Starts there, opens down through negative 1 and 4. Ignore my horrible scale on there that went wide. Function 3. The a value is 1, so this is going to open up. My x-intercepts here are going to be negative 1 and 4. We see that coming up a lot here, which means, and we've already done this one, that's going to be that my h value here, sorry, it's just going to be the same as this one above it here. For a second I thought I did the arithmetic wrong. That'll be 3 over 2. Now, in this particular case here, these two graphs are basically the same. It's just that this one opened down, this one opened up. There was this extra negative in here that made this the k value positive 6.25. Here, that's just not going to exist. So my k value is going to be negative 6.25. There's a strong connection there, which means my graph, when I plot it, I'm going to try to plot this better. Here's my negative 1. And then 1, 2, 3, 4. I hope I did that better. Negative 1 and 4. Okay. My vertex this time is going to be at 1.5. Okay, or at least my axis of symmetry will be at 1.5, and then down here at negative 6.25. Whoops. 25. And then this will open up. Good enough. Okay, much better than my last one at least. And now finally, this one right here, this one is going to open down. The x-intercepts here will be negative 4 and positive 1. So that's very, very similar to this top one up here. And notice, again, the difference here, really, the only difference between these two is that this one was positive, this one is negative. And what that's going to do here, my h value, it won't affect my h value. So that's going to be the same as the very first one I did. So negative 3 over 2, or negative 1.5. The k value, though, will take on a different value here. It'll be positive 12.5 instead of the negative 12.5 that I had. So this graph, there's my y-axis, there's my x-axis. 1, 2, 3, 4, negative 4, 1. Axis of symmetry is going to be negative 1.5. But this one here is going to be up here at 12.5 for my vertex, and this one is going to open down. And there you go. See, I hope that makes sense. I hope you can appreciate really how much information you can pull out of those equations if you just know how those points are related to each other.
Now we want to take a moment and look specifically at the relationship between the roots of an equation, the zeros of a function, and the x-intercepts of a graph.
Okay, now we just want to take a moment here and make sure that everybody's making a connection that really, really needs to be made here. There's a little bit of vocabulary here that we want you to connect, and we've probably mentioned this before, but now we're just going to be really upfront about it. There are three words, roots, zeros, and x-intercepts, okay? The solutions or roots of a quadratic equation, and a quadratic equation looks like this. Maybe I need to zoom in on that. Okay, 0 equals ax squared plus bx plus c. Notice that the only variable here is the x. Now, I know people are going to say, well, wait a minute, a, b, and c are variables. And yeah, they can take on different values, but these are considered constants in this particular function. Once they're established, they don't change. X, however, will take on various different values. And we got to figure out what specific value of x makes this expression equal to 0 after you've chosen what values are for the a, b, and c, or after your teacher has given you values for a, b, and c. Now, we can do that by factoring and by using the quadratic formula, and that's what we looked at in the first chapter of this particular course here. Now, that is going to be very, very similar to the zeros of a function, okay? Because now remember what a function is, okay? A function is this y equals f of x, okay? Y equals f of x. And when we say zeros of the function, what we mean by that is we're going to replace the y with 0. So essentially, we're going to allow our function to become equal to 0. So what happens here is our function, okay, this functional relationship between x and y here, we're interested in what happens when the independent variable, when the dependent variable goes to 0. And essentially what happens here is this expression it forces it to become a quadratic equation. And that's why there's a link there. So why do we use the two different words? Well, because we're looking at the quadratic in two different ways. This is an equation, okay? This is a relationship, a functional relationship between two variables. Now, it just turns out that they overlap at that moment here. Now, likewise, when we're talking about the x-intercepts of a graph, and you've probably already seen that, when you're talking about the x-intercepts of a graph, how do we find that? Well, we let y equal 0. Sorry, that looks like an x. We let y equal 0 and solve for x. Well, what did I just do here? In my equation, I just let the y variable become 0. Now here, the intention is that what you're doing is you're looking at all the dots on the graph. Okay, so here's your quadratic here. And what we're doing is we're looking at all the different points on the graph, and we're looking for the ones where the y-coordinate is 0. Those are the x-intercepts. But that variable right there, that x comma y, that y is exactly the same as this y. So when I let this y become 0, I'm doing essentially the same thing over here. So I let y go to 0, which means I'm letting the y in the function go to 0, and once that happens, it becomes an equation. So all three of these things are doing the exact same thing. It only depends on your perspective. What is it that you're trying to accomplish? What is it that you're looking at? How are you looking at the quadratic? Okay? So before we go on and do some examples here, just recall that, remember, y equals f of x. This is our function here. So the function is the y here, right? Y is equivalent to the value of that function that it takes on. Just remember what's going on there. Okay, so now let's take a look at some examples. Okay, so for this question here, we're told to consider the following function, f of x equals x squared minus x minus 6. So the corresponding equation of which we can find the roots would be, basically I'm going to let f of x become 0, the y coordinate becomes 0, and I get this right here. So now we're going to determine the roots of the equation, the equivalent equation here. And I can do that by factoring or by using the quadratic formula if I don't know how to factor that. But this one here should be relatively easy to factor, even by just guess and check. I know that x will break up to x and x. This one here is negative. So the two factors of 6 here are going to be positive and negative. And because this number here is negative, I know that the larger one is going to be the negative one. The more obvious factors of 6 that I see right now are going to be 2 and 3. Now that might not work. It might be 6 and 1, but 2 and 3. And I would let the larger one be the negative one, the smaller one be positive. Does that work? Well, yeah, it does, because negative 3 plus positive 2 is going to be negative 1. That's going to work here. So if these two factors multiplied together get me 0, then either x plus 2 is equal to 0, or x minus 3 is equal to 0, which means x is either negative 2 or x is equal to positive 3. So now I've solved the corresponding equation. The next question says the zeros of the function are therefore what? Well, the zeros of the function will be -2 and 3. Those are the two values of x that cause the y coordinate there, or the y value, or actually, sorry, I should say it like this. These are the two values of the independent variable that force the dependent variable to become 0. That's how we discuss it when we're talking about zeros. Here, I'm just asking what values of x make this equation equivalent, okay, where this side is equal to this side. This discussion is a little bit different here. So if x is either one of these values, then f of x is equal to 0. So if you plug in, for example, -2, then in our equation we're going to get -2 squared minus -2 minus 6. Now if you're not careful with the negatives here, this ends up looking wrong here. -2 squared is going to end up being +4. Minus -2 is going to be +2 minus 6, and there it is, I do get a 0. F of 3 should also equal 0. That's going to be 3 squared minus 3 minus 6. Well, 3 squared is 9, and then this is going to be -3, -6, and yeah, that turns out to be equal to 0. So both of those values, when I plug them into the function for the independent variable, produce a dependent value that's equal to 0. Perfect. And this means that the x-intercepts of the graph of the function will be -2 and 3. Okay, now I'm supposed to verify this using technology, and I could do that really quickly here. Just pull out my calculator. Here we go. So x squared minus x minus 6, and when I graph that, and there we go. It goes through -2 and it comes up through +3. I can even just verify it by looking at it. I could go through my trace menu and look for the zeros, but I think it's pretty obvious there. If I go into my table of values, actually this isn't probably even a better way of doing this. When x is equal to 3, the y coordinate is 0, and if I check up at -2, yep, I'm getting 0. So those are my two x-intercepts. Okay, so for this function, or this question I should say, we're asked to consider the function 2x squared minus 7x plus 3. The first question says, explain how we can find the zeros of the function algebraically and graphically. Well, algebraically, okay, we let f of x equal 0, okay, which means letting the dependent variable, okay, it takes just a second or two to write this, the dependent variable be equal to 0. Then we solve for the independent variable. Okay, we solve for the independent variable by factoring or the quadratic equation. Quadratic equation. Now, that's if you're going to do it algebraically. If you're going to do it graphically, we're going to enter the function into our calculator, our graphic display calculator, the GDC, and we use, okay, in this case it's going to be the 0 function to find the x-intercepts. And we've done examples of that already. So that's what's going on here. So now this question here, the next part of this question says determine the zeros of the function. Well, I'm going to do this one algebraically because I think this probably requires more practice than the graphical solution. So I'm going to let f of x go to 0, and I get 2x squared minus 7x plus 3. And I'm going to want to factor this. Now, I would normally look at this first by trying to pull out the common factor, but there are no common factors. But I'm going to do this by guessing and checking, because 2x squared and 3, well, those are beautiful numbers, okay, because they're prime. So they can only be broken down into 2 and 1, and 3 can only be broken down into 1 and 1. Or sorry, 1 and 3 here, that's it. Because this is positive, I know that both of these factors are going to be the same sign, and because it's negative, I know both of them are going to be negative. 3 can either be 1 and 3 or 3 and 1. Okay, now if I put the 3 and the 1 here, 3 here and the 1 here, then this is going to be 2 and 3, and those will not combine to get me 7. But if I put the 3 here and the 1 here, then I'm going to get 6 and 1, and those do combine to get 7. So this is how it's supposed to be factored. And then either 2x minus 1 is equal to 0 or x minus 3 is equal to 0. Bring the 1 over by changing the sign, and then I divide. So x is either 1/2 over here, or x is equal to positive 3. And those are going to be the two zeros of the function, okay? So we might even say over here that our zeros are 1/2 and 3. There we go. Okay, this question asks us to algebraically determine the x and y intercepts of the graph of f of x equals 3x squared minus 11x plus 10. Okay, well, first of all, let's do the low-hanging fruit, the easy one. We're going to do the y-intercept, because all that requires of me is that I make the independent variable equal to 0, okay? So I'm just going to make x equal to 0, and that's going to be 3 times 0 squared minus 11 times 0 plus 10. Now, because of the zeros as factors in both of those terms, those are just going to disappear, and I'm going to be left with 10. So the y-intercept here, okay, the y-intercept is 10. Now my x-intercept's a little bit different. I'm going to let the dependent variable go to 0, and that's going to give me 0 equals 3x squared minus 11x plus 10. And now this is an equation that I got to solve. Okay, well, I'm going to try guessing and checking right now, just because 3x squared can be broken into 3x and x. Now, for my factors of 10, probably 2 and 5, maybe 1 and 10, I don't know. But this is positive, so they're both the same sign, and this is negative, so I know they're both going to be negative. Regardless of what happens, I know that's true. 10 could be 2 and 5. Now, if I put 2 and 5 here, 2 and 5, that's going to be 2x and negative 15. Sorry, negative 2 and negative 15. That's not going to get me 11. So I'm going to swap it. If this is 5 and 2, this will give me negative 6, negative 5, and there's my answer right there. Because negative 6 and negative 5, when you expand the outer and the inner products here and add them, I will get negative 11. So that's it. So now either 3x minus 5 is equal to 0, or x minus 2 is equal to 0. So 3x is equal to 5, x is equal to 5/3, or x is equal to 2 when I solve each of these little equations. So my x-intercepts here would be 5/3 or 2. And now finally, algebraically determine the x and y-intercepts of the graph of the function f of x equals x squared minus 8x plus 8. And again, let's go to my y-intercept first because it's easy. So I'm going to let the independent variable become 0. So 0 squared minus 4 times 0 plus 8. And just as we saw with the last one, that just collapses down, becomes 8. So the y-intercept here is 8. Now for the x-intercept, we let the dependent variable become 0. And that's going to get us 0 equals x squared minus 4x plus 8. Okay, and now I'm going to run into a wee bit of a problem here, because my factors of 8 don't add up to negative 4. Okay, factors of 8 are 2 and 4, or 8 and 1. Well, 2 and 4 won't sum to 4. 8 and 1 will not sum to 4, which means factoring won't work here. What I'm going to end up having to do is the quadratic formula, and that's really why that's here. So my a value is 1, my b value is negative 4, and my c value is 8. And so now I'm just going to plug that information into my quadratic formula. So the negative of the b value plus or minus the square root of the b value squared minus 4 times a times c all over 2 times a. So this is going to end up being the negative of negative 4 is positive 4 plus or minus the square root of 16 minus 4 times 8 is 32. Whoops, I should have another parenthesis right there. All over 2 times 1 is 2. Now I can already see there's going to be a problem here, but let's take it to the next step here. This is going to end up being 4 plus or minus the square root of negative 16 over 2. Okay, well, I can't get a real number by taking the square root of negative 16, which means there is no point on the coordinate plane where that is going to be true, the real plane here that's going to be true. So as a result, we can conclude that there are no x-intercepts, and that's totally fine. All that means is that this parabola, when it opens up, has been moved so it doesn't intersect the x-axis anymore. Okay, it's going to look something like that. Okay, something like that. Anyway, I hope that makes sense. I hope that kind of helps you with your understanding of the factored form of the quadratic function.